Heatsinks are devices that absorb and release heat from an object in contact. They come in various shapes and sizes. The aim of this project is to find the perfect heatsink for a given problem statement. Parameters like varying base and varying height affect the heat dissipation capabilities of the heatsink. Copper has a higher thermal conductivity than aluminum. This means that copper is better at absorbing heat and conducting it away from the heat source. But that doesn't always mean that copper is always the best choice for a heatsink material. The way a heatsink is designed, that is its shape, size, the spacing of its fins, also have a large impact on its effectiveness, and an aluminum heatsink with a good design can outperform a copper heatsink with a poor design. Every second your processor generates heat. Too much can harm performance. Here's where a heatsink comes in. This is passive cooling, where the heatsink absorbs and disperses heat naturally. For higher performance, we add a fan. This is active cooling. It helps the heatsink dissipate more heat, keeping your system running smoothly. Heatsinks have a wide range of application. For example, the stepper motor used in 3D printers produce enough heat to damage itself on the long run. A fin heatsink is used here, designed to effectively absorb and disperse the heat. Similarly, a radial heatsink is employed for high torque DC motors, which allows for maximum contact and efficient heat dissipation. We started brainstorming and finally decided to start by breaking some appliances that use heating elements. After running through a couple of appliances, we found the ideal circuit for our application in a toaster. After some more discussions, we got to work. The nichrome tape's resistance attached to one of the mica sheets came out to be around 15 ohms. So we started to test the model out using different nichrome wire patterns and different resistance values, which is directly proportional to the length of the wire. Some of the iterations worked well, some didn't. Spiral patterns made it possible for us to confine the wire in a small area. In one of the iterations, there was too much resistance built that it was too much for the toaster to handle. It ended up blowing a copper trace along with the solder out. But after soldering a bridge and changing the wire, everything was back up and running. Now it was time to convert the toaster circuit into the nichrome heater. Made a quick trip to Ace Hardware to gather some components. At Ace Hardware, we found a wealth of options in nuts and bolts. The selection was vast, catering to any and every need. Here is a list of components that went into making the nichrome heater. The nichrome heater was finally ready to be tested. Connecting the nichrome wires to their terminals, we see the heater performed well. After designing a template for the nameplate in Adobe Illustrator, it was time to laser engrave it. With the nichrome heater ready, it was time to move on to the test bed. The first iteration had two mica sheets kept in distance between a wooden block. The nichrome wire would be wound to the mica sheet without touching the wooden block. An aluminum plate would be placed above the heat source to heat up the heatsink, and a fan would be used to demonstrate active cooling and passive cooling of the heatsink. To put our idea to test, we first try to wind the nichrome wire on mica sheets. Everything looked good until the wood caught on fire due to extreme heat from the wires. Then we decided to add brass spacers and use air to separate the sheets. This resulted us in coming up with two configurations based on nichrome wire threading pattern in the mica sheet. Once the testbed design was finalized, we made a model in Fusion 360 to start our build. Back to the laser cutter. Mica sheets were also laser cut based on illustrated designs. Here, aluminum plates or brass plates would be used to give a structure to the testing bed. We went through quite some trouble cutting aluminum. That is until we stumbled upon the metal cutter, which made it look like cutting paper. And after a little drilling, the plates were ready to be stacked. Once we had all the required components, we started the assembly of the testing bed. Threading nichrome wire turned out to be a tedious task due to its flexibility. But finally our test bed was ready. Well, the test didn't exactly go as planned, so had to unbind it and find it again. During the test, we noticed that the current passing through the nichrome wire caused the wires to expand and cause a short circuit in the system, which ends up melting the wires at a few contact points. It was time to check the next configuration out. It's much easier to wind in this configuration, and we also switched nichrome wire with nichrome tape, which had a firm structure, making winding it through the mica sheets easier. The test bed worked perfectly and surprisingly good in both the configurations. Only that was left to do was to get heatsinks to test the heating bed. And with that, we had everything to begin our experiment. these are the heatsinks we will be performing tests on. So here's the experiment. We place the heatsink on top of a thermal pad glued to an aluminum plate. The nichrome heater then heats up the test bed, which in turn heats up the heatsink. When the heatsink reaches 140 degrees Celsius, we turn the power off and record the heatsink's temperature as it cools down using a thermal imaging camera with and without using fan for all the tests. We perform the same test on various types of heatsinks and note down readings. We had a complicated setup behind the scene, of course. From case 1, we compare 3 heatsinks of middle density type of varying fin length. The video is sped 1.5 times to arrive at this time lapse. Here, we see how each heatsink performs without a fan. And now observe the improved performance when we add a fan. Moving on to case 2, we have 5 other heatsinks which share the same base and height but vary in terms of fin design. Like in the previous case, it is evident that adding a fan which is active cooling always makes the heatsink cool down much faster. Now let's perform a few calculations to arrive at some results. We've got the heat transfer equation, which tells us how much heat we're gaining or losing. Then there's the heat transfer rate, showing how fast this heat exchange is happening. Lastly, we have the cooling rate, indicating how quickly our temperature is dropping. From case 1, we see that the cooling rate increases as the area exposed is increased. This is demonstrated by varying the length of the fin from 10 to 15 to 20 mm. However, we do see some peculiar results such as MD4015B performing better than MD4020B without a fan. This might be due to the fact that a larger heatsink can trap more heat and thus there is more heat to be dissipated. But when a fan is introduced, MD4020B outperforms the rest. From case 2, the MD4020B heatsink has the highest cooling rate with and without a fan. The MD4020B heatsink, despite having the lowest mass and area, has the highest cooling rate per gram of material without a fan. This makes it the most efficient cooling per gram and per unit area heatsink. However, with the fan on, it exhibits the lowest cooling rate per gram. For all the heatsinks, the cooling rate increases with the use of a fan. From the results, we can see that not every heatsink performs the same despite similarities in dimension. The middle density heatsinks are designed for moderate heat transfer, making them ideal for scenarios where you have a balanced mix of airflow and heat dissipation requirements. Low pressure drop heatsinks are built for minimal resistance to fluid flow. These are ideal in situations where the airflow is relatively low, like in passive cooling systems or tightly packed electronic devices where you don't want to disturb airflow while still cooling the components. Standard elliptical fin heatsinks offer a balance between heat transfer and pressure drop. Omnidirectional square pin fin heatsinks are designed to enhance heat transfer due to their geometry. They're best for systems with multi-directional airflow and high heat, such as high-performing computer servers or power electronics. Omnidirectional hexagon pin fin heatsinks provide more surface area compared to S-type if it had the same number of protrusions, increasing the surface area. In conclusion, the MD4020B model provides the most efficient cooling both with and without a fan. The other models might be less efficient at cooling in these particular scenarios. For those of you looking for a more detailed exploration, we've got just the resource for you. This site offers an in-depth guide to choosing the ideal heatsink. It covers topics like thermal resistance and capacity and highlights the need to consider factors like ambient temperature, power dissipation, and allowable temperature rise. You'll also learn about different heatsink materials, thermal conductivities, and the use of thermal compounds to enhance heat transfer. Choosing the correct cooling solution could vastly influence your outcomes. Whether you're piecing together an advanced gaming console or creating robust machinery for industrial purposes. Thus, it's vital to invest time in thorough research and pick the right heatsink. Thank you for watching.